2 minutes to go. That's so that it's going. Okay, don't misbehave. Okay. Masks on so that the spies who can see us.
Oh, yeah.
We have to have masks here because we are in person at Imperial College. See, I have an astronomy. I like your, it's very nice. Okay. But you realize you've not got it in landscape mode, but I guess that's okay.
Yeah, no, I'm just trying to get this right. But I don't quite know how.
Well, because you've not got it in landscape mode, it's going to always come out a bit funny.
Oh, I see.
That's all right for us. We've got a great big screen here. It's like being at the movies.
I can get this better.
So Wesley, are you a graduate student with Claudio at the moment?
No, I'm a PhD student in Brazil, and I went to Boston as a visiting scholar for a year.
Okay, very good. And so are you now broadcasting out of Brazil or out of Boston?
No, right now I'm in Brazil since January.
Oh, wow. Okay, cool.
Yeah,
Which city are you in Brazil?
Sorry?
Which city in Brazil are you in?
Yeah, I live in the south of Brazil, a city called Cambé. It's,
okay,
yeah, I mean, probably like the closest thing that you might know is São Paulo, which is like around like a 1.5 hour plane trip.
Oh, wow. So you really are far on the south. Okay.
No, yeah, a little bit. You guys are like, you were talking about Rio de Janeiro like the other day, right? So it's like, I don't know. It's
a 2-hour flight from Rio, is it?
Yeah, a 2-hour flight, more or less.
Oh, wow. Okay.
It's a bit far.
Yeah. Okay. Well, welcome to Madam the City. I wish we could host you here in London. In fact, one of the people here, Andrew Ho, has a postdoc who's just arrived from Brazil into London. But he had to go and do the full 2-week quarantine in some very fine London hotel.
Oh. Yeah, it isn't all that bad. Let us be honest. Where's my page now?
We'll give it a few minutes whilst we wait for the audience
to get this right.
You can adjust things. So what is your affiliation, Wesley?
You mean the university where I am?
Yeah, that's right.
Oh yeah, it's called the State University of Londrina. It's like the city, like right next to mine.
Londrina.
Londrina.
Let me write that down. That's very good. Londrina is like a sister city to London.
Oh yeah, it's like some people say it that Londrina is like a little London or something like that. There's some people around here like to believe in that.
Oh, you made it. Yeah. How is your?
Yeah, everything's good. There's always a risk that I get kicked off Edirome, so the more people on it, the better.
Okay.
Yeah.
I can make you an account. It might be a bit.
Yeah, it's too late now. I'm not gonna. Oh, you can leave me an account. That's right, just in case I desperately need it. In the past, it's linked me back on again, but we'll see. Okay. Well, we're going to give it a few more minutes.
Okay. So just to be sure, how much time do I have?
You have 90. Actually, I'm going to just double check because today's a funny day.
Yeah.
Okay.
So 1 hour.
1 hour in total. Okay.
Okay.
Yeah. So in that case, and that includes time for questions. So it's a shorter time today because we've got 3 speakers.
Oh, okay.
So let's roll the hang on. So today we are running from 1:30 to 2:30 our time. So yeah, okay, let's kick off then. Welcome everyone to Condensed Matter in the City. We are continuing today with 3 talks. The first is by Weslei Fontana and Claudio Chamon. Then the second will be by Frank Polman, and the third will be by Andrea Young. We are traversing the world today because Weslei is a collaborator with Claudio Chamon. He's doing his PhD and broadcasting from Londrina, which is the Federal University of Londrina, which is in the south of Brazil. And today, Wesley is going to continue the theme started by Claudio in his talk earlier in the week, and he's going to tell us more about Fracton topological order, but now in the continuum. So welcome, Wesley, and we look forward to your talk.
Okay, thank you. So I'll make a continuation for the Claudio's talk that he gave like Monday. And what I'm interested in talking about today is about like fractons, but from a continuum field theory perspective. So fractons is this topic that like is quite hot right now, where like have many branches, like in very different kind of fields, like in theoretical physics. So Claudio discussed a little bit like of the spin liquids perspective of these fracton models, but they can extend it, they can be understood as well, like from the point of view of higher Hengage theories, where Seiber and Schau did a lot of work on it, and many other people as well. Fractons have they also have some like connections with gravity, elasticity theory. And one perspective that is quite interesting as well is this idea of foliation, where the space-time is foliated in some way in which like the fractons characteristics emerge like in a very nice way. In this talk, what we are trying to do is like to start from a lattice model, like some spin liquid model, and we are trying to define a map between the lattice and the continuum in order to obtain the continuum field theory for a lattice model in a systematic way somehow. And then we will see that these theories that emerge from this prescription that we're going to talk about today, there are usually of a Chern-Simons, a funny Chern-Simons, and sometimes the BF the kind of theories. So in the current days, these fracton models, they are classified in 2 types. Either they are type 1 or either they are type 2. In type 1 models, the fractons, they are understood as like single particles. They are unable to move. These are usually called the fractons. But in these kind of models, some bound states, they have the ability to move under certain restrictions. So for example, as Claudio was talking like on Monday, some of these models, you are unable to move a single defect on the lattice, because as you try to move, there is an energy gap between each step of its motion. So you have to like give some energy to the system to move a particle in some direction. So in each step, you are creating more and more excitations. And therefore, if you try to move these particles very, very far away from in the lattice, you need like a stable like income of energy to the system in order to make these guys move. But if you try to move, for example, bound state of 2 excitations in the lattice, you see that in each step of its motion, no new excitations are created, and these guys can move freely along some directions in the lattice. Usually these bound states that can move along some directions are called lineans, because they are some sort of a one-dimensional particle. And you can even have like these guys that are called planians, which are interpreted like a finite size excitation, in the sense that is like a plane that can move, a plane of excitations that can move along one of the directions allowed in the lattice. Some models that exhibit, like that fit in this type 1 classification, are the Chamon model, the X-cube model, and some like these are, I believe these are the most famous ones. And in type 2 kind of Fracton models, there is the complete lack of string operators, in the sense that given two excitations, you cannot build an operator that connect them, and as a consequence, like can be interpreted as the word line of that excitation. So in these type 2 models, if you try to move any excitation in the lattice, you will find that there is no operator able to do that. So this means that not only single excitations are like confined, but also all kinds of bound states cannot move in any direction. So these models, they are completely, any excitation built in a type 2 model, they are completely immobile. So an example of a type 2 model is the encode, which has, let me see. No, yeah, is an example of a type 2 model is the encode, on which all excitations are immobile. Also, another funny property of these models is that they exhibit like an extensive ground state degeneracy. So the degeneracy of these models usually scales with the length of the system instead of the area or the volume, as one might naively expect. And so this is an unusual behavior from the point of view of continuum field theory, because this will lead that any continuum field theory for a Fracton system also has to have a degeneracy of this form. And this implies that the degeneracy in the continuum will diverge as we take the continuum limit.
Wesley, sorry.
Okay.
Okay. There is someone in the chat asking whether you can go full screen.
Let me. Oh, okay.
Thank you.
Okay, sorry. Okay. So our goal today is to like define a prescription to obtain these theories in the continuum. I want to find a way to start from a lattice model and write down a consistent effective theory for these Fracton systems. So some of the ingredients that these theories might have, need to have actually, is that, like as I just said, the ground state degeneracy for these models, they have to have a linear dependence on the length of the system, which means that in the continuum limit, they have to diverge somehow. These models on the lattice, these models will exhibit some kind of exotic global symmetry, in the sense that they will not like simply have a global conservation, a charge that is globally conserved, but other higher rank charges, in the sense that not only charge is conserved, but also like dipoles and quadrupoles and so on. These on the lattice will somehow like correspond to the subsystem symmetries that these models usually present. And also from the continuum perspective, this is already a hint that the gauge structure, like for these theories that we are going to write, it can't be as usual with linear derivatives and so on. They have to be, they need to have more complex structure in able to describe these these extra conservation and exotic symmetries that the model present. And as a check of consistency, we want to match like the operators in the lattice and with the operators in the continuum, which means that any kind of operator that appears on the lattice needs somehow to be mapped in the gauge invariant operator in the continuum. So for example, if I have two dipoles on the lattice, two defects, as I try to move these two defects, I can define like a rigid string that describes this motion. So the string operator on the lattice must somehow correspond to a line operator in the continuum and so on. So these are like some of the things that we expect from these theories in the continuum. And now we proceed to try to build a systematic way of finding these theories. So these lattice systems, usually they are defined with a Hamiltonian of this form. So you have like some sort of a stabilizer operator. You can have many kinds of it, in the sense that this alpha index, it runs from 1 to how many operators you have on the lattice. And usually for the systems that we are interested, these operators, they square to 1. So they are a realization of a Z2 algebra. And as Claudio mentioned, like in his description of the lattice, these operators also are like commuting projectors. So they have to commute among each other and they have to square to 1 for every alpha and beta and for every position as well. So this alpha index, it like refers to how many operators I have like on the model. For example, in the Dirac code, alpha equals to 1 means that I'm looking for the blackhead operators, and the other like index for alpha is I'm referring to the stars. In the X cube, alpha can run from 1 to 4, which means that I'm looking at the cube excitations of the cube operators of the X cube and the 3 possible stars that I can write in that model. So typically these operators that are of the form, like some sort of a product of these spin operators that appears on the lattice, and I'm using this gamma representation because they can, like it's some like representation that I use for these spin operators, and so it can be like simply like for example, when I have like a 2-dimensional local Hilbert space, I can represent these guys via Pauli matrices. If I have like a higher dimensional local Hilbert space, I can get some Dirac representation for these stabilizers. So just to give an example, in the Claudio's model, these guys can be thought as the product of 6 operators along the faces of the cube. Like, so I have to imagine that I have like an FCC lattice, and in each face I place a spin operator, which I'm representing as a Pauli matrix. And in this notation this generalized notation that we are putting here, these operators can be written down as these gammas, which I will like just identify with the corresponding Pauli matrix. So this I index simply runs like along the lattice, and I can simply identify with the given Pauli matrix that sits at that position. And I think I wrote it. No, I think I put it down there. Okay, so yeah, I didn't insert the notation for these, but I'll get to that like in a moment.
Wesley, can I ask you a question?
Please.
Yep. So in the case of gamma matrices and sigma matrices, the operators anti-commute. at a given site. Is that a general property of the gamma matrices in the more generalized models, or not?
Sorry, can you repeat, please?
Yeah, the gamma matrices that you've given examples of are Dirac matrices or Pauli matrices, and these anti-commute at a given site. Is that a general property?
Yes, it will be. In order to build these Fracton models, all the operators that appear like in the product for the stabilizers, they all have to anti-commute.
Oh, okay,
So
thank you.
These gammas always will be anti-commuting.
Right, thank you.
Okay. So just let me see if okay. Yeah, I make a mess with this presentation. Okay. So these gammas in general, they will be represented as follows. They will be represented as like a gamma matrix at a given site to a power of like a vector that will say either there is an anti-commuting operator at that site or not. So in general, those gammas that appears on the stabilizers, they're given like as this. So they can, so these are like anti-commuting operators. They can be like some sort of a Dirac representation, and either there is a Dirac matrix at that site or not. It will be set by the components of these T vectors that I'm inserting right here. So I want these, like, since these will be composing the stabilizers, I want these guys to square to 1. And due to the algebra of these guys, they will also, like when I multiply every like guy in this set that I'm considering, they also multiply to 1. This property, like if I think in terms of Pauli matrix, this property is simply the product of all Pauli matrices that is proportional to the identity. But when I represent the lattice operators in this form, what do I get is that since they square to 1, these vectors that I'm using to identify them, they are defined only mod 2. And the fact that they all multiply to the identity tells me that this all these T vectors that I defined in the exponent, they have to sum to 0. So there is a linear dependence on these vectors. So as I said, for the Chamon model, this is simply saying that I'm doing like I'm making a different representation for the spin operators in the lattice, and then I'll identify the corresponding Pauli matrices and associate a T vector to that guy. Okay. So the idea of like representing this way is because I want to propose that like this, what I'm calling a bosonization scheme, where I will assume that these gammas can be represented in terms of these exponentials. And later on, I want to find what kind of algebra these A objects they have to obey. And in the continuum, I want to associate these A objects with the corresponding fields of the continuum description. So right now, I'm just assuming that the spin operators can be represented in this way, and I want to find what kind of properties these A objects here they have to obey in order to be a faithful representation of the spin operator. So a crucial property is that these guys, like the lattice operators, they anti-commute, and these, if we demand that this still holds for this representation, this tells us that these fields, they have to obey these commutation rules. Together with this condition, which tells us that essentially this K matrix that I'm plugging here, it has to be anti-symmetric. So this is simply saying that in order for these operators to be anti-commuting, the A's have to be, they need to have this commutation rule. And these vectors, together with this matrix, they have to obey these conditions. And in addition, these models also have like an extra condition, which is that if I take this stabilizer at a given, like displace it from an epsilon, this parameter epsilon, and I take these to 0, I'm simply saying that when I take all the spin operators of a given stabilizer and I collapse every one to a single point, they have to square to 1. So for example, if I consider this simply the simple blackhead with 2 x's and 2 z's, I'm simply saying that when I take the continuum limit in which these guys are all collapsing to the same point, this operator has to be the identity. This kind of property can further constrain the structure of the T vectors, and this is like this will be an important property to find a consistent effective theory. So just as a warm-up, just to try to make these ideas a bit more clear, I want to start with the Wen plaquette model, and I want to apply this prescription and try to obtain an action, like a continuum action for this model. So the Wen plaquette model can be defined as with this Hamiltonian, in which these stabilizers, they're a product of these Pauli matrices. So this is simply, you have like a plaquette operator and you're multiplying all the spins in that given plaquette. So we can represent this model with our gammas like this, choosing these vectors. So like these vectors are chosen in order to represent these 3 Pauli matrices. And this last one is simply saying that we are taking for example, we are representing the Y matrix here as a product of X and Z. So when we do that, we can think of it like this. So from the perspective of the lattice, you have a square lattice with 2 possible sublattices, which I'm represent of black and red. These operators are simply saying that you have like an X, and a ZZ that comes from this plaquette, and this guy will contribute with an X, a Z, and Z to this given site. So you always have this kind of encounter of spin operators in a given site. So we can demand from the algebra of the local operators, we can ask that Z and X have to anti-commute, like from these both plaquettes. And when we do that, we can find the commutation rules associated to each of the fields that will be correspondent to that given plaquette. So the commutations that we are requiring is that the field that comes from this plaquette anti-commutes with the field that comes from this plaquette, and so on. We can group these commutations simply in this guy, when I'm plugging this matrix here just to differentiate from the red and black plaquettes, and they have to be given as this. All right, these are the commutations that follows from the requirement that this local algebra holds. And when we apply that prescription of the representing the spin operators with the explanation, and take the continuum limit, we can write down the Hamiltonian as follows, where this cosine comes simply from the Hermitian conjugate that we have here. And this funny derivative that I wrote here is simply a contraction between these t vectors that I defined before with a linear derivative term that comes from the expansion from the spin operators. That comes from the expansion of these operators on the lattice. So this will give me a field that is evaluated of the position x plus x, and I'm doing a Taylor expansion and collecting
Weslei.
corresponding terms. So,
Wesley,
please.
can I ask a question, please?
Please.
Yeah, can you explain to us, obviously to take this continuum limit, the A's have to have some kind of smooth configuration. Is it at all obvious from the starting model that there's a rigidity to the A's that will allow you to do this?
What do you mean when you say like a rigidity of
Well,
A's?
I mean, you didn't, first of all, I'm at a disadvantage because you didn't explain your continuum limit step. But I presume you're making some assumptions that there is a smoothness of your variables A to do this.
Yes. Mm-hmm.
So is there a reason to believe that the A's will be smooth? Can you see that from the Hamiltonian? It's just not obvious to me. Is that because the number of visons or fractons is very low at low temperatures? Is that the reason? I don't know. Could you explain, please?
Okay, I think that at this moment I just assume that this continuum limit like holds. I don't think.
Well, is there a physical reason to suppose it's a reasonable assumption?
This is just what this Maserati Chamon behind me.
Piers, if I can chime in a bit.
Sure.
So this is actually checked a posteriori because the A's, there is, if you actually ask that these operators, these vertex operators, they retain the property that, for example, when you expand the Pauli matrix, it squares to 1. And if you want this property to, the A to inherit this property, these A fields would actually change in steps. So they would be, say, 0 pi. And so which will make them not necessarily smooth at the short distance, right? But if you look at long distances, you would expect that it would form a surface. So your question is really, really good, but I think this was actually checked only a posteriori, because in the sense that this is a bit like a solid on solid model that you can take the continuum limit, but you in principle you would need a lock-in potential that would tell you that the A is actually changes only in steps.
Okay, thank you.
Okay. Okay, so considering that the continuum limit can be taken without problem, you can obtain this Hamiltonian. And the effective theories that we are interested are the ones that describes the ground state of these models. So I want to pin this quantity to 0. These can be enforced in an action by means of a Lagrange multiplier. And when we do that, we obtain the following action. So this first term is needed to ensure the correct commutation rules between the A's. And the second term is to enforce the ground state constraint. So these two objects that I plugged here, like the A0I contracted with this A matrix, is the Lagrange multiplier that imposes this constraint. And in fact, this is just like the BF theory in 2+1 dimensions. We can work these indices out, and then we can write down these actions as follows. We can simply put it in this form. So after we've done that, we see that like the effective theory for the model is just like this BF theory with a given like a K matrix that I'm writing as this W. Okay. So the idea is that like, at least in 2+1 dimensions, this seems to work just like, this seems to work fine for the one plaquette model, because we already know that like for that given model, the action in the low energy theory is indeed given by this action. So you want to try to extend these ideas to 3D models and try to see if we can, in fact, describe the Fracton theories, the effective theories for these Fracton models. In particular, I want to find the effective theory for the Chamon model, which is like the easiest example that we could thought. Okay. So the idea is that once again, we start from the stabilizer operator. So in the case for the Chamon model, it is given by these octahedras, and the Hamiltonian can be written down like in the lattice as this. So if we apply the same prescription as we did before, we can write down an action of this form. Where these funny derivatives are now, they are not linear, but they are given by these combinations of second order derivatives. Gauge symmetry is now a little bit different, because now you have like that the spatial components of these fields, they transform with this funny derivative, and they are linear in the time direction. Which induces this funny continuity equation for the, if we plug this field theory to a conserved current, the continuity equation that we need to ensure that this current is conserved is of this form. This follows from this gauge symmetry. And now we want to examine what consequences emerge from the gauge structure being different from what we usually have. So immediately from that continuity equation, we observe that there are some global conserved currents, which are given as the integral of the whole space of this density of charge. But there are also more conservative quantities that we have to examine, which are given by this conservation of charges over codimension 1 manifolds. So if we look at this continuity equation, we can write down these terms as what I'm calling the D13 plus, D13 minus, which is simply defining a new coordinate that is given by this, with this sigma being plus or minus up to a constant, right? So this tells me that if I integrate over these planes, like defined by these coordinates 1, 3, and 2, 3, I can still have like some notion of a conserved charge that is now not conserved over the whole volume, but over this codimension 1 manifolds. These can be tracked down to the lattice as like the subsystem symmetry that the model presents. So so in fact, now any charge configuration that we want to build in that effective theory, it has to obey global conservation of charge and this conservation over all these subdimensional manifolds that we can build. Okay. So this is a first property of these effective theories that effective theory that we wrote down, and we want to see if it captures some of the universal properties of the lattice model. So one of the important aspect of these models is that they have to be the excitations. Any kind of charge excitation that I build, it need to have some sort of a restricted mobility. And in fact, the mobility restrictions that we have in this effective theory can be understood by means of analyzing these line operators that emerge because of the more complex gauge structure that we have. So we can build these gauge invariant operators, which are like the lines associated with that theory. And we see that these guys, they can be understood as representing the dipole mobility of excitations in this model. So this guy will be gauge invariant if you attach a dipole to each end of the string along these x13 directions and x23 directions. So these, from the lattice perspective, they can be understood as the mobility dipoles associated with the subsistence symmetry of the model, which is, let me find here, which can be understood as follows. So these line operators that are defined in the continuum, they can be tracked down on the lattice as these lines where the dipoles can move. So this is the coordinates that are arranged in this way. And so those lines corresponds exactly to the mobility of dipoles along these directions, and so on for each of the possible planes that we can analyze. So in this sense, we have like the line operators are being mapped in these guys here in the continuum. And in fact, the last property that we want to understand is the ground state of degeneracy, because since the model in the lattice have the extensive degeneracy that we mentioned before, we want to understand how this degeneracy emerges in the continuum. And what we can do is to consider that we take all these planes, these codimension 1 manifolds, in which charge is also conserved, and we consider that as a hint on how to foliate the theory. So if we take our 3+1 theory and foliate along these planes of where charge is conserved, we can obtain like a usual Chern-Simons along these, in each of these 2+1 we can obtain several 2+1 theories along these planes. So the idea is that in each of these 2+1 dimensional theories, I know how to compute the degeneracy associated with a Chern-Simons term, and then which will be finite in each of those planes, and then we sum over all the possible planes that we can build with this foliation that we made. So the length dependence will arise because of this foliation structure, and in each of these planes the degeneracy can be computed as usual as one does for a Chern-Simons theory. So we can consider the action associated with the zero modes of the gauge fields that we have. The number of layers can be associated with the length of the system plus the lattice spacing. And when we compute that, we simply find when we compute that, we find that for each plane, the degeneracy will be 2. So the degeneracy for the stack will be 2 to the n. And since we have 4 such stacks, because there are in 3 dimensions, we can build the 4 pairs of planes. And so on. There are 2 others. And therefore, the ground state degeneracy for the entire system is just 4 times this quantity, which can be simply written as this, where this L is like the length of the system divided by the lattice spacing. And this is exactly the degeneracy associated with the Chamon model on the lattice when we have all the lengths of the system equal to one another. So in this sense, we are finding that the relevant line operators and extended operators in the lattice are being mapped into a good representation in the continuum, and that the degeneracy between the 2 theories is still holding nicely. So in this sense, before I go on, in this sense, we are arguing that this action of these funny derivatives really describes the low energy physics of the Chamon model. So by means of these mappings and this weird gauge structure with this funny conservation laws, we are saying that this is a faithful representation of the Chamon model. And in fact, we can extend these ideas to higher dimensions. And the way we do that is by taking these gamma operators and find bases of Dirac operators that are still anti-commuting. So when we do that, you find that in order to build a higher dimensional version of these guys, we can do that using Dirac matrices, but we need to find a set of Dirac matrices such that all the operators, all the Dirac matrices in this set, they are all simultaneously anti-commuting. So one can check that, and what you find is that the sets that will have this property are all even dimensional. So you can only find a good set of Dirac matrices that are all simultaneously anti-commuting with the matrices in that set and with no other that are not in the set, if you consider set of 3, 5, 7, and so on constituents. So in this sense, the higher dimensional versions of the Chamon model, as we built, they seem to be consistent only if we consider an odd dimensional spacetime. No, an odd dimension spatial generalization. So in order to maintain the gap of the system, we have to also include more stabilizers, because we are now, as we go to higher dimensions, we are increasing the size of the local Hilbert space. So we need more operators able to label all the states in this higher dimensional version of the model. And so
Wesley,
yes.
can I just let you know that we only have 14 minutes left, including questions. So if you want question time, please bear that in mind. Okay.
Okay, yeah, I'm almost over. I think this is my last slide probably. So yeah, it is now that we now have like more operators in order to label all the possible states in the system, because we're now increasing the size of the local Hilbert space. But and therefore we can build these guys. They still commute with one another, which will give the same conditions for the fields that we have before. So the effective theory is obtained in a similar fashion. So we do the same steps. We restrict find the computational rules associated with this field to impose a term that gives the commutation, the correct commutation rules that we found before, and one that gives the ground state constraint for all these stabilizers that appears on the Hamiltonian. So now we have alpha stabilizers in the Hamiltonian, and therefore we need to impose alpha constraints. We need alpha Lagrange multipliers. But different for now in this d-dimensional case, these fields, they have to be d+1 dimensional vectors. And funny enough, even though we are in higher dimensions, the derivatives that are relevant to describe the physics of the Chamon model are still second order. So even though we go to a higher dimensional description, the physics is very similar to the three-dimensional case, in the sense that we still have like the conservation of charge over the entire volume of the system, but also the conservation over the codimension 1 manifolds and nothing more. The only difference is that we now have more sub-manifolds in which charge is conserved. So the continuity equation can be written down pretty much in the same way as before. And just because I'm running out of time, I just want to plug like the last few properties for these higher dimensional models. So charge is still conserved over the entire system, but over these several codimension 1 manifolds, the relevant operators in order to compute, for example, the ground state degeneracy are still given by the lines, but now we have many more of them, but they're given in the same way as they were given before. And funny enough, the ground state degeneracy still scales only linearly with the system length. So even though we go to higher dimensions, the dependence of on the length of the system of the ground state degeneracy is still scales only linearly and not with a power of this guy. And okay, yeah, this is pretty much everything I wanted to say about these constructions. So if you guys want to ask questions, because I probably rushed a little bit with this whole talk. So I think that now is a good moment.
Well, let's first thank Wesley for an interesting talk. And let me welcome questions either in the chat or by raising your hand in the participants list. Okay, Gunnar, would you like to ask a question?
Sure, yeah. So it's just kind of trying to go over some things in a little bit more slowly so I can follow. So could you re-explain exactly what determines which submanifolds have additional conservation laws, and how do you derive that, please?
How do I derive the additional conservations?
Yes, please. Yeah.
Okay. So you can think, let's take for example, the 3D case. So from the continuity equation, I can write the continuity equation essentially like this. So if we consider a closed manifold in which, like,
could you just define your derivative status, that d1 minus d3?
Oh, sorry.
Yeah.
So, they're essentially defined like this. Minus sigma, yeah, where this sigma is plus or minus. So they're simple, okay? So the idea is that if we integrate over the entire system, we can find a charge as usual, which is conserved given that we can like ignore like boundary terms associated. So this is like just the usual charge conservation that we find in any field theory, like in standard literature. But now, because of this weird form of that arise because of the gauge structure, you can also think of integrating along these manifolds over these directions. So if we consider, for example, an integral over a plane like this, and given that like these and the fields obeys like sufficiently fall off conditions, like if they fall off sufficiently fast, you can like ignore the boundary terms, and therefore you also find that this charge is conserved given this form, and many more, like the other three as well. So the way I'm thinking of this charge conservation of subdimensional manifolds is simply by integrating these continuity equations over these other planes that are permitted because of the structure of the derivatives. Does that help?
Yeah, okay, yeah, I think that makes it kind of a little bit clearer. So it's, yeah, so it's linear combinations that come in here that define kind of the normal vectors that are special, right?
Very simply that. So when we consider that like charge over the entire volume has to be conserved, and also these subdimensional manifolds, in fact, you can like restrict a lot of the kind of excitation that you can create in the model. In the paper that we've made, we showed that these guys, that the form of this, the allowed charts that you can build are essentially the quadrupole excitations in the lattice model, for example. So these two conservation rules, like the fact that the charge has to obey these two, has to be conserved over these two kinds of manifolds, in fact kills the creation of like single dipoles, for example, or like the creation of a single excitation.
Wesley, can I ask an idiot question? Normally, continuity equations give you conservation laws because you have a total divergence, and then you can use. So I don't see the total divergence in your expression for d by dt j0. Could you just show that to me pedagogically, how dx dy dz of j0 is a conserved quantity?
Yeah, the way
I mean, it should be a total divergence. I should be able to just use the divergence theorem and just replace things by surface integrals. But can you just show how that works?
Yeah, perhaps like one
for the Q you just gave us.
Yeah, the one form of the continuity equation that might help is that we can also write it down with the t vector. Like, let me think.
No, it's taking the equation you wrote above. Could you just show how it's a conserved quantity? That equation here, yeah, the D13 minus D23, D2. It should be obvious, but I just can't see it. Could you just explain why the total volume integral is a constant of the motion?
Wesley, I think you need to use that. It's the integral of total derivative. If you integrate over the.
I just can't see that though. Can you?
Yeah.
Oh, okay. You were okay.
Uh,
So, for example, you can think of the equation written down as this. So when you, for example, integrate over the entire volume, you will always obtain a surface term. So, for example, integrating of the x dy dz. In each of these, independently, like in each of these, you end up having like the dx of J1 evaluated at the boundary, or the dz of J1 evaluated at the boundary, and so on. So,
okay.
So what we consider is that like that in this sense, like these guys will also give like a similar condition as a typical continuity equation. So for example, I mean, if you integrate the entire thing, you'll have like, it will be like different integrals for each of these terms. But in this sense, you can still think that they fall off sufficiently quick. And
Can you integrate in the submanifold? Like the second conserved quantity? I think that's what Piers wants to see. If you take the second conserved quantity and you show that it's also, you can do a.
Just staying with this, I can see that if I take the x integral, I have the dx squared of the J1, but that doesn't help me with the other terms. And so you're then saying I've got to do the y integral. I'm sorry for being idiotic here, but it's still not clear to me. Can you do the dx integral and show how it works for all of the components? Obviously, the integral over dx of the dx squared term gives you the difference of dx of J1 at either end. But what about the other three terms? Do you then, I guess you do the dz for the dz one and.
Oh, okay, yeah, it's something, yeah. So for example, if you have this, we are taking this integral, so this will give a surface term.
In the x direction of that term.
Exactly. And similarly for the other, so for example, if you take the dz, dx dy dz, this will give us like a similar thing, but for the x direction.
Okay, I got you now.
Yeah.
Okay.
And
Thank
therefore,
you for explaining that.
we can.
And for the submanifold, it would work similarly, right? If you want to show for the submanifold.
Yeah, for the submanifold, we just. You can, for example, take, let's take one component just for simplicity. Let me think.
You have to take charge of it. I can't look at my screen, right? So what's next? That's the next talk.
Next talk is at 2:45.
Okay. Right.
So, let me see. No, I think that this is a bad choice of. Let's take, for example, D13 plus, D13 minus. And do 3 plus D3 minus, and integrate over, for example, 13 plus plus. Yeah, we have to be a little careful with like the fact that these guys are not orthogonal to one another, but essentially we can up to overall constants, we can simply like take the derivative of this first guy, because like these two are orthogonal to one another. So when we take the first integral, this will give like a surface term for the and the 3 plus. This will give a surface term for the J1 analyzed over the endpoints of the x1, 3 direction, and similar thing for the other, which will give a
Good, thank you.
2, 3 plus, and so on. And also in this sense, we still have like the conservation in a similar fashion as in standard field theory.
Good. There's a few more questions. We've got just a little bit more time left. Gunnar's asked one. Adam has a question.
Hi, sorry. So I know the models you were talking about are very different from the Haar code, but if you just tried to formally go through the same steps for the Haar code, do you know what would happen?
In fact, yeah, you can do a similar thing, but in the Haar code, what happens is that when you start with the lattice, for example, you take like the Haar cube, you have like 2 cubes, in fact, right? And you do the same steps that we did to obtain the field theory. The theory will still be of a Chern-Simons term, and we will still be of a Chern-Simons form, but naively, the field theory that you obtain still have like mobile particles. So what we did for the Haar code is that apparently you need an extra constraint for the field theory of the Haar code. So you cannot simply do the same steps and obtain the effective theory. And when you try to match the operators in the lattice and in the continuum, you simply can't, because the continuum limit is admitting the existence of string operators, for example, which can be associated with the mobility of some excitations. So what we did for the Haar code is that apparently you need an extra constraint in order to ensure immobility of everything. And this extra constraint that we took, it emerges because when we collapse this cube to a single point, this gives us an extra condition for the t vectors that we considered, and it somehow gives us a condition that you have to project. You have like a Hilbert space, and you have to project on the physical Hilbert space, so a subdimensional Hilbert space, and only the excitations within that like smaller Hilbert space are in fact immobile. So with our prescription for the Haar code, you obtain a theory that in principle admits like the mobility of dipoles, but when you take this extra constraint of the fact that the cube collapses to a point, and that gives another linear dependence of the t vectors, that extra constraint kills all possible string operators that you can build. So in this sense, you can argue that within this subdimensional Hilbert space, all excitations of the field theory that we wrote down are indeed immobile. Does that help? I mean,
okay, but I mean, do you think it in principle makes sense to have a field theory for the Haar code, or I mean, does the very weird degeneracy in that model and stuff mean that there won't be? I mean, or are there some things you can capture with a field theory?
No, yeah, I think that it makes sense, but it's tricky because, I mean, for example, for the Chamon model that we analyzed here, we analyzed the matching of operators the kind of excitations that can appear in the model, and the ground state degeneracy. But the degeneracy for the Haar code, it's like simply weird. If you it can give like different things. So from the field theory perspective, it seems very non-trivial to find the correct degeneracy for that model. But in the sense that we can write down a theory that at least captures these properties related to the mobility of the excitations and the form of the fractal membranes that appear on the Haar code, we can write down an action that like apparently seems to capture all of this. But
okay, thank you.
Let me just add one thing to Adam's question. So in this paper, we did the construction from the lattice to the continuum, and when you go there, you get this Chern-Simons action, but you need an additional constraint from this product of the cube multiplying to 1 that comes as a constraint in the physical space. So coming from the lattice, we couldn't write just a pure field theory that will have all the ingredients. We needed this extra projection. Now, what the projection did is eliminated one of the derivatives, so killed the dipole propagation. So you went from type 1 to type 2. But we also learning that you have to kill one of the derivatives. We construct a continuum model.
Claudio, can I just interrupt? We've only got 5 minutes.
I know,
Claudio,
but let me just.
We've only got 5 minutes, so can you wrap it up, please?
I'll finish in very quickly.
Yep.
So the bottom of that is that you can write a continuum field theory for a type 2 model with that one less derivative, but we don't know a lattice model of which that continuum model would be a representation. So we don't even know if there is a lattice model. So.
Thank you.
Okay, thank you, everyone. We're going to take a 5-minute break now. Let's thank Wesley one more time. Thank you for a great talk, and see you all in about 5 minutes. Okay, bye-bye.
Thank you, bye.